Yeah, I can do set. Oh, yeah.
Okay. I think we're done.
I think you're still muted and the mute button is still on.
No, that's red if it's muted.
Oh, okay.
Now we can share the screen. This one.
Here.
Yeah. That PowerPoint. Or you can do whole screen, entire screen. Okay.
Oh.
All right.
Oh, that's all the people who are receiving it. Going through that.
There's an infinite recursion.
Yes, it is.
Okay, we can start.
Okay.
Just
Please.
click. Yeah, you.
Who is it?
Oh, who's that? Okay, you want that? Yeah, that one.
Okay. I will just click on this one, right, to start. Okay.
Oh, it's a feedback. I think you can present to present everyone, and then you can just so you have to go to PowerPoint and just continue. Yeah, full
This
screen.
one?
Full screen.
Right.
Slideshow. Yeah, this one.
Okay. Oh, sorry about this.
We should start 10 minutes before. Yes,
That's right.
Yeah.
Next time we know.
Sorry about this. Yeah, analyze that. Okay. So today I'll talk about the influence of the mesoscale oceanic ice in the crucial extinction region on the North Pacific storm track. It is based on part of my thesis. So let me first start with some introduction of the recent studies of this mesoscale Earth interaction. The picture here shows the small scale SST and surface wind in the crucial extinction region. This is calculated based on the high resolution satellite data. The colored shaded is the wind speed, and the contours are the SST. So we can say that the warm SST anomalies actually corresponds to high surface wind speed. This picture suggests that actually the oceanic ice has some influence on the atmosphere surface, and there are also a lot of many other studies that indicate that shown that the oceanic mesoscale ice actually can also influence the surface turbulent heat flux and the boundary layer height. So my studies is mainly concerned about if besides the influence within the boundary layer, is there deep response in the atmosphere to this oceanic mesoscale ice? And the second is that if this oceanic ice can have the further influence on the Pacific storm track and the larger scale patterns. If so, what is the dynamic mechanism behind? So, to investigate these problems, we set up two sets of Wolf-Olin simulations. The first one is the control run, which contains 10 ensemble members, and it is forced by the high-resolution observational SRT. The one snapshot of the SRT is shown here. And the other simulation is called filter run, and which are all the settings are exactly the same as the control run, except that at the SST, the low boundary is forced by the smallest SST, and the way we filter the SST is using a spatial filter, and this picture here shows the SST difference between these two simulations. We can see that the largest difference is confined in the crucial extinction region, which represents the oceanic eddy activities. So next we want to see.
I was trying to say that.
Should be okay. Sorry about that.
So we next want to look at how the atmosphere will respond differently to these two different SST photon, including oceanic eddies and excluding oceanic eddies. This picture shows the total rainfall difference between the two simulations. This one, we can say that in the crucial extinction region, when we remove the oceanic eddies, there's a decrease of rainfall change along the crucial extinction region. This suggests that the influence of this oceanic eddies is not limited to the boundary layer. It can actually penetrate deep into the troposphere. And the other very interesting result that is there's also a remote rainfall response along the west coast of US. And we further separate this total rainfall into convective rainfall and the non-convective rainfall, which is shown here as these two figures. It turns out that in the crucial extinction region, the decrease of the rainfall is mainly due to the convective rainfall, while in the along the west coast of US, the increase of rainfall is mainly due to the non-convective rainfall. For the convective rainfall, it is more related with the local convergence and divergence. So the picture suggests that if we remove the oceanic eddies, it somehow stabilize the boundary layer and prevent the development of convection. On the other hand, the non-convective rainfall, which is more related with the large-scale synoptic storms. So the rainfall change along the west coast of US suggests that there is some change of the storm track or large-scale atmosphere circulation. So when we checked the mean flow and the storm track difference in the two simulations, the top left figure is the mid-latitude jet simulated by the control run, and the right figure, the top right figure, is the jet difference between the filter run and control run. We can see that in the filter simulation, there is a southward shift of this mean flow. The bottom left figure is the surface storm track. Because the major feature here is that there is a significant decrease in the along the crucial extinction region when we remove out the oceanic eddies. And for the right figure is the up-level stump track. So the most significant response is actually there's a southward shift of the up-level stump track downstream in the Eastern Pacific Basin. So we next try to explain why there's why this stump track change happened. So there are two theories that are related with the cyclone genesis. One is the dry volcanic instability theory, and the other is the moisture volcanic instability, shown in the shown as the left and the right figure. So according to the classical volcanic instability theory, the stumps usually develops above sharp temperature gradient region in the frontal zone due to the summer-winter relationship. The left figure here shows that when a cyclone passes by a strong temperature gradient region, at low level, this cyclone actually will advance because the north is cold temperature and the south is the warm temperature. The cyclone will advance to warm temperature anomaly just ahead of this the cyclone. So the central line arose is the initial state of the cyclones, and when there's a warm temperature anomaly ahead, it has a low pressure center which will induce a positive PV anomaly, and this positive PV anomaly will add back onto this original positive PV, which will intensify this cycle, the cyclones, which shown as the double line arose. So the intensify the cyclones in the lower level will further positive feedback onto the up level, which will together make the stump to growth. This is for the dry case, and in the wet case, there's additional to this warm SRT anomaly. There's additional diabatic heating release by moisture, which will add another PV source to the cyclone, to the low-level cyclone, and this will further intensify the stump growth. So, in a word, that in the wet atmosphere case, because of the additional source of diabatic heating PV, it will support a stronger stump growth. So we next try to see which of these two theories actually explains our case.
This is basically an ED type of model, ED model.
Yeah, it's based on the ED model.
So the cyclone genesis theory? No, this is like very general.
But the basic idea is the tropopause and surface interaction.
That's right. This is Hoskins. Yeah, it's just the PV positive feedback between the low level PV and the high level.
I think the dry case is basically the ED based on the ED model, right?
Well, basically it's a theory for the generalization of the theory for the for maximum instability.
So when they first check this dry volcanic instability theory, the dry volcanic instability is mainly associated with the temperature gradient, and these two figures, the SRT Folsom in the controller and filter run, and this figure here shows the zonal average temperature profile in the crucial extinction region. The x-axis is the temperature, and the y-axis is the latitude. So we can say that in the two experiments, the temperature gradient is almost the same. There's no significant change. In addition, we also checked the ED growth rate, which is a measurement of the surface baroclinic instability. It is the ratio between the vertical window shear and the Brunton Väisälä frequency. Again, in the crucial extinction region, we can say that there's not much difference between these two simulations. This suggests that the storm genesis in the crucial extinction region is the weakened. What do we see here? The weakened storm genesis is not due to this dry baroclinic instability theory. So we then hypothesize.
Did you also compute the ED growth rate at another level? Or you only computed the AD?
It is the H surface. No.
You didn't compute it?
No. Yeah.
Maybe worthwhile checking and plotting the things at another level.
Okay. So we then hypothesize is mainly made due to the moist baroclinic instability theory. So in the moist baroclinic instability, the case is that there's additional diabatic heating release due to the moisture supply, and so the figure here shows the diabatic heating difference between the two simulations. You can see that in the crucial, there's a lot of small structures. In the crucial extinction region, we did see a reduced diabatic heating in the filter simulation. So this supports the moist baroclinic instability. Also, we checked the water content in this region, and we also see a decreased water vapor mixture ratio in this region. And this right figure is a vertical profile in this zonal band, and the latitude is a vertical line.
You can hide that. The height.
Which one?
The height.
Bottom.
It says
Oh, height. Okay.
Yeah.
The x-axis is the longitude, which from 20 to 50, I think. And the y-axis is the pressure, the height. You can see that the temperature, the moisture decrease is mainly confined below the 700 millibars within the boundary layers, suggesting that this water vapor is coming. Is coming from the ocean surface. When we remove this, the ocean adding, actually there's less moisture supply from the ocean, which will decrease the diabatic heating, and this, according to the moisture baroclinic instability, this will decrease the storm growth. To validate the storm growth rate in the two simulations, we plot the storm evolution in the control run and the filter run. This is shown in the two columns. So this is from the lag 2 day to 2 days before and 2 days after the storm passing by the crucial extinction region. Lag 0 means that the storm is passing this crucial extinction region. The lag equals -2 means that it's 2 days before the storm passing the crucial extinction region. Like I said, in the control run, the storms originating from the continent, it gradually grow and reach their peaks when they pass in the crucial extinction and then gradually decay. And in the filter run, it's similar, but it's with a much weaker amplitude. We then, to further clarify the storm evolution, we plot this evolution time series. This is the variable plot here. Actually, is the amplitude of the center of the storm. So the red line shows that the storm growth in the control run. The blue line shows the storm growth in the filter run. And we can say that it is normalized by the the lead to day values. So if we start from this point, we can say that in the control run, actually stem grow faster, which suggests that the stem in the control run indeed has a stronger growth rate. We have shown that in addition to this decreased stem track at surface in the crucial extinction region, there's also a remote response of the up-level stem track and the mean flow. We then try to explain this remote response using the eddy-mean flow interaction theory. So here the figure. The right column figure shows the eddy kinetic energy in the control run, filter run, and the difference between these two, and it is which represents the stem activities in the simulations. In the control run, we can say there's a maximum eddy activity just downstream of the crucial extinction region after the explosive stem growth, and in the filter run, the stem is further developed downstream into the Eastern Pacific. In the crucial, it is less developed, but it has a further momentum deposit into the Eastern Pacific. We then introduce the E vector, and it's to measure the eddy-mean flow interaction. The divergence of E vector actually give an estimation of how of the energy transferred from eddy to mean flow. So the positive value means a divergence, and the divergence of this E vector actually co-locates with the mid-latitude jet. The positive value means that there is an acceleration of the westerlies. In the control run, there's a maximum of the divergence just located in the central Pacific basin. It is following the explosive stem growth. In the filter run, because the stem is further developed downstream, the maximum divergence of E vector not the maximum, the divergence of E vector actually is stronger downstream, and it is more clear in this difference map, which can say this the downstream increase of the divergence E vector. This means the increase of this divergence E vector means that the more energy is transferred from eddy to the mean flow. This leads to the southwards shift of the mean flow, which is shown here. There's this is 300 millibar wind velocity. To further look at the vertical structure of the mean flow of the stem track and the mean flow change, we plot the vertical profile in this zonal band. The left figure is the stem track change between the filter run and the control run from the surface to up to 100 millibar, and the right figure is the 300 millibar U wind change. We can see that there's an increase of the stem track in the south, and a decrease of stem track in the north in the whole air column, which means that this is the downstream response actually is a barotropical response, but the peak of the response occurs at 300 millibar. Same thing happens in the mean flow field. This barotropic response is consistent with the barotropic decay of the storm development, of cyclone development. So yeah, that's also the changes in this mean flow change and the stump track change is consistent with our rainfall increase in this region. So the conclusion is that the mesoscale oceanics in the crucial extinction region actually can influence not only the local rainfall but also the remote rainfall. It's removal of this mesoscale oceanics. It will cause a decrease of rainfall in the crucial extinction region and increase our rainfall along the west coast of US. And the mechanism we hypothesize mechanism is the mesoscale oceanics will destabilize the planet boundary layer and decrease the latent heat release, which will enhance the latent heat release and intensify the storm genesis via the moisture-bearing instability theory and through enemy flow interaction, the storm track will. There is a southward shift of storm track and the mean flow. Yeah, that's all. Thanks.
So questions?
I have a question. You had the formula for the ED growth rate, right? Is there a similar formula for the moist theory? That there's some.
No, it is the ED growth rate is basically for the dry.
But you refer to a paper which talks about the moist parabolic stability. There's no formula.
They didn't calculate the ED growth rate in the moist.
So there's no analytical result. It's all just.
No, I didn't say.
There's a two-layer model study, the French guy. It's all numerical because the moist thing depends very much on the parameterization of convection. Depends on the condensation and heating. So the growth rate probably going to vary. Depends on how you're going to parameterize that condensation and heating. And that's really the complicated part. By the way, Xiaohui, I don't think your explanation for the go back to your Hoskins paper again. I don't think you explained it quite right.
This one?
Yeah. I just want the other student to be clear on that. So the dry instability, yeah. So you're plotting this, right? So you have this upper level vorticity coming.
Yeah.
And then which also going to influence the lower level. That part is right? So then if you have a very strong front, then this part is the warm air is going to affect it in front of the upper level vorticity, right?
Yeah.
Then that warm air is going to introduce another low level positive PV.
Yeah.
And it's going to enhance that. It is going to have an impact in the upper level PV circulation as well,
this
right?
one. Yeah.
And then what happens is upper level PV is going to evac the air from north to south in the region where maximum PV is. No, this one.
Here, right?
This one, because this circulation going this way, right?
Yeah.
So you actually have another circulation going this way. So both circulation is actually trying to have, you actually have a flow going north to south, right near the center of this maximum PV. So what happens in the atmosphere is high PV air is actually to the north. Low PV is actually near the equator. So you have that when you have anomalous advection, you advect higher PV into this region. And that's the reason why you actually enhance the upper level vorticity. Then the upper level vorticity is going to enhance this process again. And this is what he called the positive feedback.
So it is
that's really the key.
It is not the lower level intensified PV that influence the upper, further influence the up level.
No, it's actually the lower part is adding another additional advection, bringing more positive PV flow into this region. And that's the reason why in the baroclinic theory, all the wave has this vertical tilt. This tilt is extremely important, so that you can actually have this phase shift, so you can actually bring the air to this region. So that's his whole thing. So your explanation is not quite right. It's getting close, but it's not, not exactly right. And this is actually a quite, you know, I think conceptually this is very useful. The problem with this is that very difficult to quantify theoretically. You can actually do the PV diagnostic. The theory is very useful for people doing the diagnostic study. So a lot of synopticians actually using this technique to diagnose the storm genesis, because it's much easier to understand. Actually, John Nielsen Gammon is an expert on this. He's done a lot of these studies like that.
Is the atmosphere science professor?
Yeah. But then the wet process has become really complicated. Nobody knows what's going on. So you can tell what they're doing now. So what she's doing now at the moment, she's outputting all the heating term in the Wolf model. It's very complicated. So you have a shallow and deep, and you have a boundary layer heating, everything. So she now outputting every one single term. And now we're actually doing comparison between with and without eddy. You want to see which term is actually really.
So looking at the full profile.
Right. And she's also done the diabatic conversion. We have to have a meeting about this. I want to discuss with you some of the latest things we've been doing. But it's very complicated.
Chris and Hu, do you have any questions? Can you hear me?
You should be able to. Oh, yeah.
Yes, I can hear you.
Okay.
Oh, hi, Hu.
Hi.
How are you?
Good to hear your voice again.
Yeah. Sorry, I haven't got a chance to go through your paper yet, but I have a few crises here. I'll do that.
Okay, yeah. I have a question.
Go ahead.
Well, you said the ocean eddies increase the water content in the troposphere, but because there are more warm eddies than cold eddies, or what's the mechanism for that?
No, it's like actually because that the warm eddy and the cold eddy actually they have not equally effect on the water moisture. That means that the warm eddies actually has more important influence on the moisture supply. The effect of the warm eddy and cold eddy, it is not linear. It's non-linear. The residual you see is the warm effect, actually, the warm eddy effect.
Okay.
Because the warm eddy, it has the high surface SST and the lower air temperature, and so it can supply more moisture into the atmosphere. But on the other hand, the cold air, because it is colder than the atmosphere, the cold oceanic eddies, it's cold and atmosphere. It's not as efficient as the warm eddy to extract the moisture from the atmosphere.
Okay.
The warm eddy to provide the moisture to the atmosphere, and the cold eddy to extract moisture from the atmosphere. The two ways, they are not equally. The warm eddy actually is more efficient.
Okay.
That's why you see a decrease of the moisture totally overall.
So the way you do the filter is guaranteed, right? The negative and the positive will cancel because it's a spatial filter.
I didn't check, but I think overall it should, right? It's because
should be, because it's just a
it's the
like a running mean filter.
That's right.
Low
That's the reason why
field.
when you do the zonal average, you don't see any You change this
So
in the
just the
gradient.
construction, the negative, the amount of negative SST amount should equal the
right.
amount of
It's
positive.
like Fourier transformation, positive and negative has to be equal to each other, in a way.
Which is not true if you do it like Lagrangian.
Right.
That's different. In this
Right.
case, I think it has to be.
Right. Now, Jesse's results is interesting, which is different from Xue's result, and he finds actually much more antitectonic and warm eddies.
Right. But that's a different.
So that's to answer whose question, that would be another possibility. The reason the net effect, you actually see more moisture.
But here,
But here it's not, because by construction, you have about the same amount of warm eddy and cold eddy.
I have just a simple question. So these runs, how long are they done? What was the simulation? How long the simulation?
It runs for 6 months from in the winter season from October 1st to the next March.
Okay, for both of control as well as the.
Yes,
Okay.
yeah, we have 10 ensembles.
Oh, 10 ensembles.
Yeah.
Okay. So it's that was my question. Like, if anyway by increasing the number of runs, could you filter out more the noise in the atmospheric response?
Actually, we checked with 5 ensemble, 10 ensemble. The result is
don't say 5
quite same.
ensembles, say 5-member ensemble.
yeah, it's 5-member ensemble. Yes,
Okay.
and 10 members. The results are quite similar. So it's at least at this point it's not sensitive to the ensemble members.
And these, so it's only in the lower troposphere where you.
What do you mean by low?
So would the effect would be more prominent in the lower troposphere than the.
It is in the lower troposphere, and we can say that the influence of on the SST, on the heat flux, on the surface wind, on the boundary layer height. But that result is already demonstrated by many previous. So I checked that, but I didn't include in the presentation because we want to focus on the deep. We are more interested in the deep troposphere response.
Since this region is it has a lot of instability development, it does get okay. Thanks.
When I show these results in Tokyo, one of the criticism I got is actually this E vector divergence business. E vector divergence is actually very noisy. It doesn't really exactly correspond to the shifts of the jets you actually see.
It's not exactly the.
So it's
the prediction.
I mean, the same thing with Chris O'Reilly's paper. He also showed the E vector and the divergence. When you look at the change in the jets and the E vector, and you see this thing. I mean, you have a positive and negative value all over the place when you look at the difference. They don't match exactly the shift.
Right.
So I'm not sure. I'm not sure exactly how. When you look the equation itself, the eddy mean flowing direction. I mean, E vector is just one term, right?
Yeah, there's another term. There's
another term too.
Yes, I think related with F. I said.
Yeah.
Correct.
Maybe you should be more careful.
Yeah, I can.
Diagnose this, because this is not exactly coming out. The same thing with Chris O'Reilly's paper. They argued about the same thing, but when you look at the map, they don't look exactly the same. In fact, their thing is even worse than yours.
I can include the other term to check if there is some improvement.
And also, I was wondering whether it's you're doing that in the 300 hectopascal, right?
Yeah. Because we are looking at the southward shift at the 300. I will show the.
But the mean flow is really equivalent barotropic. So I was wondering whether it would make more sense to have some kind of vertical average or something rather than just look at one level.
Oh.
But for this kind of diagnostic,
Yeah.
it's hard to do a vertical average. I mean, there's always been a controversial.
Right.
Yes. There are a couple of others, the P vector, the E
Right.
vector.
They never come out to be exactly. I mean, they more or less right, but not exactly right. Kind of argument. But the mean flow change itself is actually really nice. I mean, you see a really nice equivalent barotropic response. So the question is that really due to this eddy-driven or not? Well, that's part of your PhD dissertation, Salamana, right? Oh no, your PhD is a super rotation. It's not that. Okay, very good. So
Thank you.
we still have a lot of work to do. I think still lots of things we don't understand. Thanks.
Thank you, guys. Happy Valentine's Day.
Chris, I think Chris.
Hi, Chris. Do you have any questions?
No, I don't.
Oh, you sound sleepy though.
No, I'm not sleepy.
Okay.
Why do you say that?
No, I was just, your voice sounded really tired. You can't.
Oh, no, it's just, yeah, working a lot lately.
I know. Okay. If you can send me some information about this, this supercomputer stuff.
Yeah, actually, I sent that to you just before the talk.
Okay, excellent.
Yeah.
Stop.
Yes.
You can just quit the window, probably.
All right. Have a nice weekend.
You too.
Bye-bye.
Bye.
All right.
All right.
I just stop the broadcast, right?
I'll quit. You can just quit the
Just
window.
quit.
All right.